Here we go. Properties of functions. Okay, how functions work, the important parts about them, because a lot of what we're doing, we don't necessarily need to know everything that's going on, but we do need to know what the important parts are, where the important parts are. So that's kind of what we're dealing with here. So the first part we have increasing, decreasing. Increasing, and I just put INC, increasing, the graph is rising from left to right. You always do everything from left to right, no matter what we're dealing with. So as I go from left to right, it's going up. That's increasing. If I'm decreasing, this graph is going down as I'm going from left to right. When we're talking about where something is increasing or decreasing, we talk about an interval. From where to where is it going up? From where to where is it going down? That's the increasing and decreasing. Okay, and it's always stated as an interval. Where something is increasing or decreasing, where is a function is increasing? When x equals 3, yeah, but a lot more other places than that. Okay, so it'd be like when x is between 2 and 5. And the endpoints are not included when you're doing increasing and decreasing. They're never included when you're doing increasing and decreasing. That's not what they aren't. At a particular value, it goes from here to here. It's not increasing at that point. That's where it starts to go up. This is where it ends to go up, but not at that point itself. Increasing and decreasing are always stated as open intervals. Always stated as open interval. Local max min. Okay. Local max or min is the largest or smallest value in that vicinity. It's not the global one. You will talk about, and we may talk about it here some, but in calculus we deal with locals and globals. And there's a difference between the two. Okay, you'll have locals and globals. Locals are in the immediate vicinity. Okay, if we measure everybody's height in this room, we will have a local maximum height and a local minimum height. We will have the tallest person in the room and the shortest person in the room. In this room, they are the local ones. If we include other classrooms, there are probably people that are taller and probably people that are shorter than the ones that are currently residing in this classroom. But within this classroom, we have a person who is the shortest and a person that's the tallest. They are local maximum and local minimum. If we include other classrooms, they may not be any more the maximum minimum, but within this immediate vicinity, they are local maximum minimum. On this graph, this first point here, that would be a local maximum. This would be a local minimum. In the immediate vicinity, nothing is higher, nothing is lower. In the immediate area, if I go immediately to one side, immediately to the other, that is the local max or minimum. Even if we didn't measure people by height, we lined everybody up shoulder to shoulder. If you've got somebody in the middle that's taller than the two people next to them, they are the local maximum because they are taller than the person on the left and taller than the person on the right. So they are the local extreme, the local maximum. They might not even be the tallest person in this room, but in that immediate vicinity of those three people, they're the tallest because the other two on the other sides are shorter than they are. Okay, it's only in the immediate vicinity. That immediate vicinity might be a very, very, very tiny little difference. Maybe a tiny little spot. We don't know the scale of this graph. This graph might go from negative 1 over a million to positive 1 over a million. That might be a teeny tiny little narrow graph, and the difference between where the maximum is and the ones right next to it could be this itty bitty little space. We don't know. Okay, and we have a maximum here and a local minimum here. Maximums and minimums are a point. They are an XY coordinate. The X is where that happens. The Y is what it is. The Y value is the maximum or minimum. Where they happen is the X coordinate. We're often more concerned as where something happens than what something is. And it's often easier to find the where, and when you find the where, then you can find the what. X is where, Y is what. Always. X is always where something happens. The X coordinate is where is my minimum. X does not tell me my minimum, it tells me where I can find it. Okay? Concavity. Curving up or curving down. Concave up, concave down. Concave up, concave down. Concave up, concave down. So you remember the direction of the concavity. Concave up is like a smiley face. Concave down is like a frowny face. When you're up or you're down. Okay. Concavity is the way it curves. Okay. And it doesn't have to be an obvious concavity. It just has to have a little bit of a curve up or a little bit of a curve down. And inflection points are where it changes concavity. Aiden. Hey, Aiden. Okay. An inflection point is where it changes concavity. Now, in this class, your inflection points are mostly going to be a good guess. Okay. One of the things you'll do in calculus is you'll learn how to compute these values exactly. Okay, and there are ways to do this exactly. There's a lot of work with that. Let's see, the first 3 sections of chapter 4 are all about, no, sorry, chapter 5. That's right, the book got changed. It used to be chapter 4, now it's chapter 5. Are all about this and how to use calculus to figure all this stuff out. Okay, the first 3 or 4 sections of that chapter are all about this. And so on this one, a point of inflection, you would have one possibly here. It would be right about there, right about there. It's where it goes from curving down to curving up, or from curving up to curving down, where that concavity changes. It will change at some point. Those are called your points of inflection. And they're just like maximums and minimums. They are a coordinate. Where do you change concavity? That is my point of inflection. Okay? Does that make sense? So increasing, decreasing, where it's going up, where it's going down, and max and mins, and these two are tied together here. Increasing and decreasing and max and mins are tied together. You're going up until you hit the maximum, and then you go down until you hit the minimum. You're increasing until you hit a maximum. You're decreasing until you hit a minimum. And using this graph here, I go up and then down and then up and then down and then up. So I go up to my first maximum, down to my first minimum, and then up to a maximum, down to a minimum, and then up and on forever. Okay. Is it possible for a graph to not have a maximum or minimum value? It is. Think about the work you do with parabolas. The parabola opens down in both directions. There is no maximum, there is no minimum value because it goes on forever. So if you have a straight line that angles up or angles down, doesn't matter as long as it's not a straight horizontal line. If you have a straight line, it has no maximum or minimum because it goes forever down and forever up. There is no value I can find that is the highest value or lowest value at any point on that straight line. Okay. A cubic will do that, x cubed. It comes up and flattens out and goes up again. It changes concavity, but it doesn't have a max or minimum. Okay. It's possible that concavities don't really change much. It's possible that if you have straight lines have no concavity to them. Almost everything else has concavity to it. Something can be concave up everywhere, something can be concave down everywhere. It does happen. Okay. Questions about any of these things? And remember, these two here, concavity and inflection points, those are tied together. So let's take a look at this. So go ahead and grab out your calculators. And graph the equation. Negative 2x cubed plus 6x squared plus x plus 3, and estimate the local maximum and minimum. And you know what? So if you do what you do to find the zeros, I gave you the handout that explained how to find the zeros. So on the TI, when you go to the menu that has where it has the list of things, and the second one down is zeros, if you look at that list, you have minimum and maximum. And you can find the minimum and maximum the same way that you find the zeros. Okay, so you can find the exact values for maximum and minimum off the graph the same way you find the exact values for maximum and minimum. If you have a Casio, it does the same thing. When you pull up the menu that has the root on it, instead of hitting root, one of those keys has max and min. And you can do the same thing there. You can find your maximums and minimum values from that. Okay, so you can do that on your calculators and calculate them exactly the same way you calculate your roots and zeros. It will do it. It's just a different choice off the menu. Instead of a zero or instead of a root, you just have to pick max or min, and it does exactly the same thing. It's the same steps, except for that one thing. Instead of picking zero, you pick max or min. Instead of picking root, you pick max or min. Everything else is exactly the same. It's really kind of cool that it does that for you. Okay. So I've got a copy of the graph right up here. And my local minimum takes place at 0.087, and it is 2.957. And my max takes place at 1.913, and it is 9.043. That is my maximum. And those are the values. You should be able to find them on your calculators using the max and min thing, which is really cool. It's cool that your calculators can do that stuff. Now, intervals where it's increasing and decreasing. The endpoints for your intervals where something is increasing or decreasing are always your maximum and minimum values, and if it goes on forever, negative and positive infinity. If it doesn't go on forever, it has endpoints, because that will happen sometimes where your graph only goes from here to here, then those endpoints will be the endpoints of where you're doing. And remember, it's an interval. So the points on my intervals are going to be those 2 points I have. Okay? So the graph first starts, my graph is doing what when I begin this? I go from left to right. What is my graph first doing? Increasing or decreasing? It's decreasing. So I'm going to do my decreasing intervals first. And this one is decreasing from negative infinity, because as it comes onto the screen, it's going down, to where is my minimum value? 0.87, 0.087, so 0.087. It is decreasing in that interval. And it is not decreasing at 0.087. It is not decreasing at the minimum value. Because it's not going down anymore, is it? It's not going up either. So the minimum value is neither decreasing or increasing. Neither thing is happening at that point. It's not going down, it's not going up, it's there. It's the only point that is not where the graph is not going down or going up. It's at the minimum and at the maximum. That's why it's an open interval for your increasing and decreasing intervals. Because the endpoints are not going up or down, but everywhere between them is. Okay, it is also decreasing where? From the maximum to infinity is also where it's decreasing. So it's also decreasing from 1.913 to infinity. That is where it's decreasing. It's going down. It's going down here, and it's going down here. Like I said, your maximum and minimum points are going to be the endpoints of your intervals for increasing and decreasing. Yes?
Why is it from 1.913?
What do you mean the negative? What?
Like, shouldn't, like, it's
What is going negative? It's going down, but what's becoming negative? The y, not the x. What is x doing? As the little ant is walking along this path, and is given a little xy coordinate to go along with everything that's on the path. Yes, the y coordinate is getting smaller, but the x coordinate is not. The x coordinate is getting larger. These are always given as x coordinates. Everything here is given as x coordinates. So you're either moving left or right. That's why it's left bound and right bound, not upper and lower bound. It's left bound and right bound. X coordinates. Okay, what does my x coordinate do? My x coordinates, the point may be falling, but it's still moving in the positive x direction, is it not? Okay. Not a bad question. And then so that's decreasing there. It is increasing between those 2 points, between the minimum and maximum. So it's increasing from 0.087 to 1.913. It's going up along there. Max and mins, increasing, decreasing, are tied together. Right? If you know where something is increasing and decreasing, you can find the maximums and minimums from that. And your maximums and minimums are the endpoints of your intervals increasing or decreasing. And the max and mins are neither going up nor going down, because it stopped going up and hasn't yet started going down yet. It's like at the top of the roller coaster. Are you going up? No. Are you going down? Not yet. You're right at the top of the roller coaster. So your maximum is neither going up nor going down. Okay. Inflection points. Where does it change concavity? Now, I don't believe your calculators will compute this for you. I don't think it has concavity or inflection points built in on your calculators, and I would seriously doubt that it would, because it's very hard to compute from a graph. When you do it algebraically in calculus, it's like, oh yeah, very easy to find. Well, relatively easy to find. So from here, I can't really do it well. What do I have to do? I got to guesstimate. Okay. Now, if this were a test question, your guesstimation, if it was close, I'd be okay. And if your guesstimation is close, I would be okay. For this one, I do know its exact value because I have done calculus and I can calculate the exact value, and the exact value happens at x equals 1. So right here is my point of inflection. It happens at x equals 1. And I do believe y is 5. Because I can do the calculus and I can figure it out algebraically, and this one's not that hard to do because I've done it lots of times. Okay, it is something that you will do then. If this was a test question and you said, well, okay, it's like at 0.9, or 1.2 or somewhere around there. If you gave me an idea that was in the vicinity of where x equals 1, I would be okay with that at this point. Okay, yes?
So you only want the x?
Yeah, if you want to give it as a full-on point, you can do that. 1, 5 would be it. Yeah, is that 5 or is that a 6? 6, my bad. It's a 6. Thank you. 1, 6. Okay. I am more concerned where than what. X is much, much more important. Where something happens is so much more important than what is happening, where it happened, than what it is that's happening. Does that make sense? X is much more important. Okay, if you gave me just x equals 1, I'm okay with that. You know where it's taking place. Okay. Now, the intervals where it's concave up and concave down are all tied into this, because the point of inflection is where it changes concavity. And if I only have one point of inflection, I'm only changing concavity one time. So everywhere else is either concave up or concave down, depending upon the graph. So everything to the right of my point of inflection, is it concave up or concave down? Is it happy or sad? It's concave up because it's happy. No smiley. I do that. Concave up. So it's concave up from negative infinity to 1. And once again, at the point of inflection, it is neither concave up nor concave down because that's where it's changing from one to the other.
So the inflection would be in the middle of the two min and max?
Generally, not always. It's not always in the middle of the minimum and maximum, but that's not a bad place to start looking. Depends upon how heavily curved it is. Depends upon the individual graph. For most of what you're going to be doing in here, getting somewhere in the middle is approximately where it happens, but it's not always where it happens.
It's where like the slope starts to change.
Yeah, it's where the slope starts to change. It's really the concavity where that point of inflection is. It's much harder to find non-algebraically. The best you're doing is a guess, honestly. The best you're doing is a guess. I calculated the answer because I knew I could calculate the exact answer. You will eventually next year. Okay, I had to calculate them. So I did that, so I know exactly, but like I said, just give me a good guesstimate. And usually halfway between them, but not always. You have to look at the graph very carefully. The maximum minimum, there could be other stuff going on in between that changes and how it curves and the slopes in between depending upon your equation. Because you can get some gnarly stuff going on. Yeah. Out where the concavity changes. Concave down from 1 to positive infinity. Concave up, concave down. It is entirely possible for a graph to have no concavity. There's only one graph that has no concavity. Straight line. And any straight line has no concavity. Everything else is going to have some sort of concavity. It could be concave up everywhere, it could be concave down everywhere. Lots of graphs do both of those things. There are a lot of graphs through that. The first one probably comes to mind is a parabola, but there are a lot of graphs through that way. It's a little bit of a circle. Circle does not count because it's not a function. It does not pass the vertical line test, does it? Yeah. This only works with functions. That's actually a good thing to bring up. This only works with functions. If it's not a function, these rules do not apply. We don't talk about it. We don't talk about with concavities with the circle because it's not a function. Any other questions? Okay. Average rate of change. Average. Average. It's the same as the slope between 2 points. The average rate of change is the same as the slope between 2 points. That may not be what the graph is doing between them. It may not be a straight line, but it is the slope of the line that connects those particular points upon the graph. That's what this is. Technically speaking, this is change in y over change in x. The change in my y value over the change in the x value. Okay. So I've got my function, g of x equals 3x squared minus 2x plus 3. And I want to find the average rate of change from -2 to +1. What that's saying is, hey, f of b minus f of a, so g of b, which is b is 1, so g of 1, minus g of -2, all over 1 minus -2. That's what I'm asking for. Yes?
Sure, have you found this one?
It was given to me, right? Yeah. Just whatever points you're given to. So I have a curve. Those are 2 points on the curve. I want to find the average rate of change connecting those 2 points. And you just figure out, you're finding the slope of the line between those 2 points. So you have to figure out what the y value is for both of those. That's what g of 1 is and g of -2. Those are the y coordinates to go with those two x coordinates. So I plug in 1 into here. G of 1, that's 3 minus 2 plus 3, that's 7, right? 7 minus, plug in -2, it's a little more complicated. -2 squared is 4. 3 times 4 is 12. -2 times -2 is 4. 12 plus 4 is 16. Yeah, plus 3 gives me 19. Thank you. 7 minus 19 over 3, because 1 minus -2 is 3. Okay. 7 minus 19 is -12. -12 divided by 3 is -4. So those 2 points, the average rate of change, it's going down 4 units, 4 y's for every 1x. That's the average rate of change. Because what kind of graph is that? It's a parabola. It's a curve. So I'm just connecting 2 points. And I'm finding what is, when I go from here to here, what's my average? Okay. Do the second one. Do B. Okay, so we'll do this again. F of B minus F of A. So, sorry, G of 5 minus G of 0 over 5 minus 0. G of 5 squared is 25 times 3 is 75. 2 times 5 is 10. 75 minus 10 is 65 plus 3 is 68. So I get 68. Put in 0, that's easy. I get 3 over 5. 68 minus 3 is 65. 65 divided by 5 is 13. Okay, this is the average. This is not the instantaneous. Yes, sir.
Didn't you do it like, I mean, you got the right answer, obviously, but didn't you do it backwards, putting 5 first and then 0? Wasn't that like
AB.
Yeah, but you put in 5 minus.
AB.
Yeah,
No, I did B minus A. If this is B, I did B minus A, right?
Oh, yeah.
It did. It'd be positive. Now, if I flopped them and I did G of 0, because wait, here's what's important on this one, is that these two have to line up and these two have to line up. It doesn't matter whether I put my zeros first, my 5 second, or my 5s first, my 0 second, as long as those two numbers line up with each other. Because if I'd done it the other way, I'd have 3 minus 68 over -5, which would still work out to be 13. Okay? So. Okay. Let's do the graph. Graph shows the weekly sales for a company over a period of 10 weeks. Estimate. Why does it say estimate rather than, hey, here it is? It might not be exact. You're kind of guessing. I had worked this out early. No, that's okay. Pooh, I lost my notes. There we go. See, I don't work out every problem. I only worked out some problems. So yeah, this is an estimate of what we're doing. It's not exact. It is an estimate. So between week 1 to week 8. Week 1 to week 8. connecting those 2 points for finding the average. The average is going to be the slope of that line. Now, on the side, it counts by 200s, not by hundreds. And the graph is a little off because I had to move some stuff, so it doesn't quite line up perfectly. So I'm going the 8th week, first week. So my denominator is 8 minus 1. My numerator are the y values at those points. So the y value at 8 is 1,000. The y value at 1 is 200. Okay, because it counts by 200s on the side. Which is $114.29, because we're talking money here, average sales. So the average sales per week is $114.29. So on average, they've gone up $114 on their sales every week. Have they gone up $114 every week? No, some weeks were good, some weeks were bad. But on average, they made money. So if you're in it for the long haul, you're good. Okay, something like, you got to remember, sometimes long haul is good, sometimes it's not. Okay? A lot of companies make money and then they go up and they go down. Sales always are never a good straight line for a company, rarely for very long. Eventually they'll start going down again. Hopefully, if you're good, it'll start going up again. Okay. Week 4 to week 7. There we go. Same idea. So from week 4 to week 7, at week 7, I'm at $800. In week 4, I'm at $1,400. And that's from 7 to 4. And you figure that out. And during that time, they lost $200 per week. Not real good. Sometimes things suck. And if you have enough savings put away or money socked away, losing a couple $100 a week for a little while isn't going to kill you. Maybe. And then week 3 to week 5. What is the average sales for that time? 0, because the y-coordinate's the same for both of them. There is no change. It's a nice little horizontal thing. Okay. Now, on a side note, like I said, I talk a lot about calculus. Okay. What we did here was what existed long before calculus. It's very easy to find the average. Very easy to find the average rate of change. What Newton did when he did calculus was figure out how to find the instantaneous rate of change at any particular time. Use the equation to figure out exactly what it's doing at a particular moment. How fast is it going up right now? Rather than finding the average. Okay, from here to here, I averaged this much change. Okay, what about right now? What about right now? What about right now? What about right now? And his work was all about motion. Things moving, in particular planets and large things moving and motion of objects. His work was all about motion. But anytime you can measure how fast something is changing, and you can calculate the instantaneous rate of change, you can apply that to almost anything. And that's, to me, the beauty of calculus. It's a good, I don't want to say basic, but it is a good basic math introduction that applies to almost everything. It was invented to solve problems in physics, but anytime anything changes, you can use calculus to evaluate it. And that's kind of the beauty of that, because it's all about the instantaneous rather than the average. That's what he was trying to do. Find the instantaneous. What is the instantaneous rate of change? What is the instantaneous rate of change? And he used calculus to prove his ideas in physics. And being able to calculate that instantaneous rate of change and come up with equations that describe that motion is what he did. And it's thus anything that changes, you can apply calculus to. So that's a lot of stuff. It doesn't have to be movement. Economics is a big deal. There's a lot of them. Okay? Questions? Thus.